Welcome, everyone, and thank you for joining us today. My name is Paul Donahue, and I will be your host. We ask that you please keep your device muted during the session, and if you have questions, please direct them to me via the chat function. We'll do our best to answer questions at the end and to follow up with any unanswered questions via email. As I think you know, these Tech Talks have been designed to provide straightforward insights into radio frequency components, the related technology, and the extra design and engineering value that is added by a custom manufacturer such as Quantic TRM. To begin today's session, I am once again pleased to introduce Quantic TRM's Chief Technology Officer, Shaun Moore. The author of 2 U.S. patents and a number of white papers and technical articles on passive microwave technologies, Shaun has been with Quantic TRM since the late 90s, and his passion for the job and for solving problems has only increased over the years, especially when it comes to resolving our customers' design and engineering challenges. So welcome, Shaun. Can you share an overview of today's topic and your objectives for the session?
Yes, thank you, Paul. As you see on the screen right now, we're going to be talking about some fundamental things about power dividers, some very, very high-level theory and terminology about how these devices actually operate. We'll talk a little bit about why you would use a power divider, various topologies of how to actually manufacture a power divider, and some of the things about how they work. What makes TRM components different from our competitors? I'm going to talk very briefly about what makes a power combiner different from a power divider, although at some level they can be used interchangeably, not always. And then I'm going to go through and go through a quick summary of what I went through today. First, let's start with a few definitions. A power divider is used to take a common signal and distribute it to multiple places. In this case over here, some applications include and could include antenna array feed networks, LO signal distribution, signal distribution between modules, or anything where you have to take a common signal and distribute it to various places within the overall network. Power combiners, on the other hand, are basically the reciprocal of a power divider, and they're used to take multiple inputs and put them on a common cable. Various sort of applications that can refer to this here are things like using multiple radios with a single antenna, or adding multiple power amplifiers together to generate higher power. TRM has basically worked on systems for all of these sorts of configurations. Power dividers are passive components, and thus they cannot create energy. They can only redirect it. A power divider directs a signal to many different places. A two-way power divider, for example, takes the amount of energy at the common port and splits that power in half. So half the power ends up on one output, the other half of power ends up on the other output. This power division is kind of where the title for the part came from. At the same point, we have to recognize that this split loss is sort of a universal language that we talk about. A two-way power divider will have half power, or minus 3 dB worth of actual insertion loss due to split loss. A four-way power divider will have 1/4 of the power appearing at each of the outputs, or minus 6 dB. Insertion loss, when you're talking about specifications of power dividers, are always specified as non-recoverable energy, and therefore it does not include the theoretical split loss. This is important to understand because if you take a look at the way that our parts are defined, we have for a two-way power divider or a four-way power divider, you may see that there's a half a dB or 1 dB worth of loss associated in that spec. But in reality, if it's a 2 dB power divider that has a half a dB worth of spec, in actuality, when you measure the through on there, you will measure 3.5 dB absolute. I think this is an important thing to remember as we are looking at from a system level standpoint for various applications. Now some really high level theory. Why not just bring 3 wires together like you would in a house to divide power? Won't that work? Well, the answer is yes and no. If you're looking for DC continuity through a network like this, yes, it'll work just fine, just as it works fine in your house when you go to tap in and put on that new porch light on your house. As you see though, however, If you with doing a little bit of math on Ohm's law, you'll see that if you have two 50 ohm outputs and put them in parallel, you're going to end up with 25 ohms at the common port, which is not 50 ohms. In a RF system, this is going to translate to a 2-to-1 VSWR. Virtually all of our networks rely on a 50 ohm system. And this is important because as we're going through the system, we have to make sure that we have maximum power transfer throughout the entire network, and we don't have energy bouncing around where we don't want it. Why is VSWR important? Because if you have a high VSWR, it means that you're taking energy and reflecting it back to the source. That is really what VSWR means, voltage standing wave ratio. It is the ratio of energy that relieves the source versus how much energy is being reflected back to the source. If you think about a wave pool, a high VSWR is the amount of energy that's reflected off of the far end of the wave pool. The wave moves down the pool, hits the end of the wave pool, and some of that energy gets reflected back. Energy that gets reflected back is what is known as having a high VSWR. If we had a very low VSWR, there would not be a wall at the end of the wave pool, and the wave would then continue to transmit the energy down across the medium. So in order to maintain 50 ohms at all the ports, what we do for power dividers is we actually do some impedance transformation in order so that when we do go ahead and put the lines connected in parallel with each other, we still end up with 50 ohms on the common port. So in reality, what we have to do is we have to take the 50 ohms on each of the outputs, transform them back to 100 ohms, and then put them in parallel again, so we end up with 50 ohms again back at the input. Now, there's lots of ways to do that, depending on the technology, and each one has their both advantages and disadvantages, and really the application and frequency will determine which one we actually go forward with. First, I'd like to start basically with a resistive power divider. A resistive power divider uses resistors to go ahead and actually maintain this network. This is a very good solution because it has extremely broadband response. These are all the resistors in there. Essentially works from DC right through as high as the mechanical layout of the circuit will allow, and not have without having any parasitic detuning happen. The downfall of this circuit is it has twice the insertion loss compared to a non-resistive configuration. In this example here, the two-way that you're seeing on your screen, the insertion loss here will be 6 dB, twice that of a normal two-way. Also, in addition to that, there is no isolation between the two outputs. As you can see, this is a Y configuration, in which case there is no, a delta configuration, which means that going from an input to an output or from an output to an output is the exact same circuit. Therefore, there is no difference between the insertion loss versus the isolation. Again, this over here works very good over a very broadband frequency of ranges. It has very high insertion loss, therefore it has a very low power handling capability, and there is no isolation between the outputs. The next network that I'm going to speak about here is a transformer-based network. These are all of our DL sort of power dividers, lower frequency or where these things typically happen, lumped element sort of power dividers. These offer very good VSWR, isolation, and low insertion loss. They also have extremely broadband performance, up to 100-to-1 frequency ratio at lower power. And when you go up to higher power units, that bandwidth does reduce. It's a compact design, especially if you're dealing at frequencies at HF, VHF, UHF, right through L-band. This sort of technology works very well for lower frequency sort of work. And really the upper end of this is about 2 gigahertz, being practical about as far as to how this sort of technology actually operates. Like I said, it is an excellent sort of configuration for doing these sorts of lower frequency sort of projects. Again, very broad bandwidth, very good RF performance, but the limit here is the high frequency. These sorts of circuits do not work very well above 2 gigahertz. The next sort of circuit we're talking about is the Wilkinson power divider, and there is a plethora of variations of the Wilkinson. What I'm going to discuss here is the very simplest version of it here, just to kind of show you conceptually how this works. Wilkinson dividers use a resonant length distributed transmission line to transform the impedance. These over here, in the simplest case here, is a single section Wilkinson, which has about a 20% bandwidth. Will transform that output impedance of 50 ohms through a 70.7 ohm quarter wavelength transmission line. 100 ohms will appear at the other end of that line, which will then go in parallel with its brother on the other side, transforming it back to 50 ohms on the common input. By going to a multi-section approach using a Chebyshev transform, these sorts of power dividers can be designed for upper bandwidths of around a 10-to-1 bandwidth using the stepped transformer technique. We can go to broader bandwidths by going to tapered line ideas, but those sorts of ideas are a little more unique. Most of the power dividers that we divide that are microstrip or strip line use this sort of approach as to how we actually build that component. Those are really the main sorts of power divider configurations that we have. We have the resistive power divider, we have the lumped element power divider, and we have the distributed line power divider. The different approaches to technologies to build power dividers have different advantages. No one technology is inherently better than one or the other. TRM uses all of these technologies here. Basically, we realize all of the printed sort of technologies in all of the technologies that are available. We do it in coax, we do it in strip line, we do it in microstrip, we do it in suspended strip line, we do it in coplanar waveguide. The only technology that we do not build here is waveguide itself. We offer, and I think that's an important differentiator for us. A lot of our competitors only use one technology or the other. They only do things in strip line, or they only do things in microstrip, or they only do lumped element designs. There aren't that many companies out there that utilize all of these sorts of technologies and freely intercombine them. There are many designs, for example, where we build half ferrite and half strip line, and that is done because ferrite has some very good advantages for certain applications. Yet there are certain downfalls, especially if you're starting to build an impedance transformer over there for insertion loss, in which case you can sometimes you can have the advantages of having a ferrite isolation transformer and a printed input balance transformer. There's all sorts of combinations that happen depending on power and all of the other sorts of parameters that and packaging that the customer might require. So that's one big differentiator that TRM has. Another big differentiator that we have here is we are very happy to do custom screening and validation of our products. So if somebody needs to have some ESS work done, we're very happy to do that. Something else that we're very proud of is the fact that we work with the customer to make sure that the packaging that we have is exactly what the customer needs. If the customer needs a TNC connector on there, we are very happy to do that. If the customer wants the connector on the side, we can go ahead and we work with them to accomplish that as well. These I think are some very good examples of how we work with our customers to go forward and actually customize these parts so they get the exact part of really what they need. I mentioned briefly, I was going to go briefly as to what the difference between a power divider and a power combiner is. I'm going to speak more about power combiners at a later session, but I did want to talk a little bit about it today just to remove some confusion. In theory, a power combiner is a reciprocal of a power divider. And all they do is they take the energy that is put into the inputs, they sum them, and it comes out of the common port. The issue that we have with building power combiners, though, is that it just doesn't sum them, it vectorially sums them, which means that if the vector is pointing in a different direction at the input, that non-additive energy has to go somewhere. And where it goes is into the isolation network of the power combiner. So things that affect that sort of how efficient that happens is first of all, is how coherent the signal is coming into it. I think then the thing that also matters there is what do you do with the energy that is not fully coherent, and things that affect that as far as how much the energy actually goes in there. So I think the thing to look at there really has to do with The frequency relationship of the energy, the phase relationship of the energy makes a big difference as to how much energy actually fully combines versus how much energy is actually thrown away into the isolation network. This is really a big reason as to why typically we don't recommend using a power divider as a power combiner unless it is in a very low power application. Um, there are some very specific things that we need to do to ensure that all that excess energy that is being dissipated within the power combining isolation network is handled properly. So the big thing here is we have to make sure that power combiners are designed to dissipate significant amounts of power for the non-coherent applications. Um, Typically what happens if we use any one of the power divider configurations that I talked about today is that usually the bandwidth has to narrow up. That is one thing, and this way we can allow us to use a little bit larger components. The other thing also we talk about here is that most power combiners that are really for very high applications are really nothing more than a 0-180 hybrid rather than a power divider per se. And then we terminate the delta port so that we can actually go ahead and have a good 50 ohm termination handling all that excess power. For some lower power applications, like I mentioned before, we can use a conventional power divider. We'll be discussing a lot of more of the details about power combining and why you would use one topology over another in a separate discussion. So in summary, power dividers have a wide set of possible applications. They provide ways to distribute or combine a microwave signal while maintaining good impedance matching at all ports and isolation between the signal sources. Power dividers can be used to combine signals. However, careful consideration must be used for the power handling of the isolation circuit. Some circuits are more suited than others for building a power combiner. And we're going to stay tuned about more information on power combining. And finally, in summary, here is because TRM designs and builds and tests products that are customized for each requirement, the customer gets exactly the right part, test data and screening that they require for their program, which means the customer can be confident of a smooth integration into their assembly. That's all I have for right now. So thank you, Paul, and you can pick it up. Do we have any questions?
Well, thank you, Shaun. And I think that you certainly did clear up a lot of the mystery that's associated with RF components in general, and with, in this case, power dividers. So with that in mind, we do have one question that somebody had sent in from the audience. And the question, Shaun, is, does the packaging we put around the part limit the types of technology that you can put inside the part?
That's a good question. Yes, sometimes it does. For the most part, I will say we can use either lumped element, strip line, distributed sort of technology in virtually any package. I think really what limits those sorts of applications really has a lot to do with the size. What I will say, for example, is if we're going to a surface mount component that has to handle high power, in those sorts of applications, a low frequency ferrite type solution will not have enough thermal surface area to dissipate the heat generated, and therefore in that sort of situation, I'll say no, we probably couldn't use a ferrite based device in a surface mount application. We could, however, use a strip line application in a surface mount application, because in that case we can go ahead and rework that package to get a good thermal transfer from the bonded strip line package out to the outside world. So I think in that case over there, I think we certainly could do something along those lines. Just kind of two examples. We certainly can what we need to do for each possibility is go through and really work out in detail what the customer needs and what the solution is, to see whether or not any one particular package will work for any one particular application.
Terrific. Thank you, Shaun. So once again, thank everybody for joining us today. If you are a customer who'd really like to ask more questions or maybe get more information about not only power dividers, but any of the RF components that we've talked about, please feel free to call our engineering hotline. That number is 888-677-6877. Again, that's 888-677-6877. And let me just reiterate that our goal really is to learn more and understand what your ideas are and to help you complete those ideas into manufacturable solutions. If you're one of our field reps, then you know you can call us anytime. You can deal directly through your CAM, or you can pose questions directly through the field sales rep portal that's on our website. And finally, our next tutorial session will be on focus on power combiners. Thank you, Shaun.
Thank you.